Hello everyone. In this lecture, we are going to discuss carbon-based composites that are beyond CFRPs. So CFRP or carbon fiber reinforced polymer, these are, the most important or industrially relevant carbon-based composites, and that's why we first learned about them and the manufacturing techniques that are used with them and the challenges that we face when we are manufacturing. So this is something, okay, this is just one type of carbon fiber, carbon-based composite. However, that is not it. In fact, that is just one very small class. If you think about the classification of carbon composites, then there are so many different types. For example, instead of polymer matrix, you can also have just a carbon material as the matrix. You can also have metal matrix. You can also have ceramic. You can also have concrete as matrix. In fact, carbon reinforced concrete is a very important industrial structural engineering material. So there are all of these materials. What we have learned till now is just carbon fibers inside a polymer matrix. Okay, if we want to classify carbon-based composites, then how do we do that? Okay, we can either you know that composite materials have one additive and one matrix phase, so you can do the classification based on the additive as well as based on the matrix. Okay, so this is in fact it is done in several cases. The additive that is most commonly used is carbon fiber. So in many cases when we talk about carbon-based composites, we are often talking or thinking in terms of carbon fibers because, well, of course, these carbon fiber ropes and fabrics, they give a lot of mechanical strength to your material, and that is why you can also make laminates using them. So that is why they are very common. However, they are not just the only reinforcement material, as I said. So what you can do is, number one, you can either classify these composites based on the matrix material or even the additive material. Now again, within the additive material, you can do it, you can classify based on the shape or the structure of your additive. So I just said that carbon fibers are the most commonly used additives, but you also have tubes, you have particles and so on. Okay, you even have sometimes 3D structures made of carbon fibers. And then you can, so any complex structures can also be added as the additive inside your matrix. Okay, you can also then classify your composites based on the size of the additive. So even within carbon fiber, we learned that we have short fiber and long fiber based composites. We also have fabric, because when we make laminates, then we have these fabric like structures rather than just single threads or yarns. So based on this also, now the size in all these cases actually varies. Sometimes you have just nanoscale carbon materials. For example, if you have carbon nanotubes, these are nanoscale materials, these are your additives. Sometimes you have micro scale, so if you have carbon fibers or the yarns of carbon fibers, then you're talking in micrometer scale. Then you can also have millimeter scale when you're talking about the fabric, or when you're talking about, as I said, more complex structures like 3D shapes. So based on that also you can do the classification. And finally, you can also classify your carbon based composites based on the functions of these carbon materials. So you have certain carbon materials like carbon fibers, you can call them relatively traditional materials. So they have certain functionality, they provide mechanical strength to your structures, but you can also induce new functionalities. For example, you can use graphene flakes as additive as well, and these graphene flakes, you can then have certain chemical function, or you can provide it a certain structure which will provide it certain other chemical functionalities. You can even mix fullerenes, Buckminster fullerene and others. So you can also mix these curved carbon structures, and they have very interesting properties. They have, for example, several chemical properties, even photovoltaic properties. We are going to learn about them when we talk about carbon nanomaterials. So the idea is that we can classify our carbon based composites in various ways. But our goal right now is to learn about other carbon-based composites. Since we've already learned about carbon polymer, we will now, in this particular lecture, we are going to talk about carbon composites mainly. But then we'll also talk about other composites. However, it will be relatively brief compared to CFRPs and maybe carbon composites. Also, I'll go into the manufacturing aspects. But the rest of them will be, I'm just going to cover their introduction, maybe some applications. Because anyway, you can understand that you already know how to make carbon fibers, and you know that what are the properties that are important when we make composite materials. So in that case, you can even design your own composites, and you can come up with some new matrix material, okay, or new functionalities in your additive. Okay. So yeah, that is these are the things that I have already told you. Now, carbon composites that we are going to discuss in this particular class. Typically, carbon composites are carbon fiber based. Again, so the additive, of course, you can also call, if there is some carbon nanotubes in a carbon matrix, that's also carbon matrix, carbon composite. However, most commonly used or industrially used carbon composite is carbon fiber in a carbon matrix. Okay, so how do we make them? So before we go into how to manufacture our carbon composites, let's first think about this. Why do we need carbon composites at all? Why not CFRP? CFRPs actually offer much higher mechanical strength compared to your carbon-based composite or carbon matrix composite. You can also get a lot of flexibility, which you may not be able to get from, because you can already imagine that if you have carbon matrix, that matrix is not going to be as flexible as your resin matrix. So why do we actually need these materials? Well, think about a resin and what temperature can it withstand? Most of the polymers resins would degrade at 300, 400 degrees. Even if you make certain advanced polymers, you come up with new types of resins. Even then, 400 is sort of the limiting factor. And after that, your entire material would degrade even before that temperature. As soon as your polymer goes above its glass transition temperature, you will start to lose sort of the integrity of your overall composite material. So you cannot use them for high temperature applications. And high strength is often required for high temperature applications. For example, if you want to use even for aircraft applications, even for a number of engine parts and so on, what you need is the material to be able to withstand higher temperatures and not just provide mechanical strength at room temperature. So that is where we can use our carbon composites or even other types of carbon-based composites. Okay. So as I already mentioned, there are not just carbon fiber-based, other carbon material-based composites as well, but industrially, carbon fiber mixed inside a carbon matrix is known as carbon composite. This is again the most commonly used material. Now I'll show you this diagram, which is very interesting. Here you see the comparison of strengths of a lot of engineering materials, not just carbon-based, carbon fiber-based composites, or not just composite materials, but also a lot of engineering materials. So often it happens that if you want to propose that, okay, I can make this structure using carbon fiber or carbon fiber-based composites, you often are asked, how does it compare with other engineering materials? Why shouldn't we use nickel or titanium or a certain super alloy? Because for metal-based materials, the manufacturing processes are rather well established. That is not the case with composites. So we learned also in the previous lecture that we don't have all the standards. We also don't have, we are just coming up with a lot of, although composites have been used for almost, 3 to 4 decades. But still, compared to, the manufacturing with metals, this is a very, very new material, or these are very new materials. Okay, so here you can see that, first of all, let's compare our CFRPs. CFRPs are here. You see that you can get very good strength compared to other materials. This offers some of the highest strengths. However, the application is limited to, as I said, 400. Even 400 is too high. Between 300 and 400, typically most of your polymers would degrade, or their properties will change. Okay, so this is number one. Now you see other materials here, other engineering materials. You see other metals, so aluminum, nickel, titanium, and so on. There are also certain special type of alloy materials which are based on, or composite materials that are based on silicon, aluminum, oxygen, and nitrogen. So these alloys are also, they are high performing alloys, but now they're they can withstand higher temperatures, 1000 to 1200, but then their mechanical strength is limited. So there are pros and cons of using all of these materials. our carbon-carbon composites, they fall here. And this includes all kinds of carbon-carbon composites. Here I've not shown just carbon fiber based, but even whatever advanced carbon composites we are designing nowadays. Even within carbon fibers, you can have high performance carbon fibers or general purpose carbon fibers. We are going to discuss in a while. So this is where our carbon-carbon composites fall, and you can see the temperatures they can withstand are very high, from 1200 up to 1800. And when we talk about withstanding the temperature, that basically means without any deformation, without any structural changes. So basically, at these high temperatures, your material does not lose its integrity. It is stable at these high temperatures. However, as I mentioned, compared to CFRPs, the mechanical strength is relatively lower. But since the research is going on, so you see that this line is going up. So hopefully we'll come up with some carbon-carbon composites in a few years that have better performance. So this is a very active area of research, because this is also very important for manufacturing applications. You can imagine, you can actually think of, and just write it down for yourself, which applications would require very high mechanical strength, at the same time high temperature applications. Let me give you one hint: gas turbine blades. So these are the kind of structures that operate at very high temperatures, and they operate continuously for several even for several months together, and they have very harsh environment, corrosion, and all kinds of stresses. So these applications actually require materials that are, people are often using silicon carbide and super alloys for manufacturing these kind of blades, but carbon-carbon composites can be potentially used there, of course, because they will also offer a lighter weight. So that is one advantage anyway with all the carbon materials. Okay. Yeah. So I already mentioned that you can actually have good strength up to 3000 degrees centigrade, but in non-oxidizing atmospheres, and that is something that is a challenge. The oxidation of carbon-based material, surface oxidation. We are going to discuss this as well, and there's some potential solutions to it. One important aspect is that in many cases, the mechanical strength of your carbon-carbon composites actually increases with temperature. So that is one very interesting property. So you can already imagine these are very useful materials. Okay, so as I mentioned, you can have high performance carbon fiber and also general purpose carbon fiber. So what you call them HPCF and GPCF. These are the terms you will hear commonly. So this has nothing to do with composites. It's about the carbon fiber itself. But this terminology is more used in the composite manufacturing industry. So here I have shown this big chart where you can see there are different types of carbon fibers. We already discussed that we have two important properties. One is the tensile modulus or the Young's modulus, and the other one is your ultimate tensile strength. So both properties are important. For some fibers, the pan-derived carbon, for example, you have a higher ultimate tensile strength, but relatively lower Young's modulus. But in the case of mesophase pitch derived carbon fiber, basically the graphitic carbon fibers, you have a higher Young's modulus, or often it is just called modulus, higher modulus, but lower tensile strength. So now you can already see that we can distribute these fibers, and we can say which ones are relatively low quality, and also quality would then determine the value. So low value and high value carbon fibers, those which fall in this region, they are your high performance carbon fibers, and those that fall somewhere here, they are here and so on, they are general purpose carbon fibers. If you also want to see this diagram can also be further modified, you can add more things to this. For example, you can also see where do your vapor grown fibers fall. So here we were all in this diagram, mainly we are talking about commercial fibers that are spun, melt spun or electrospun, but you can also have, for example, your vapor grown fibers that will mostly fall somewhere here in this region. So this is not these are regions, not exact numbers. And then also, of course, based on the heat treatment temperature, based on few parameters. You can also have few changes to, but these are the more or less the regions where you see where does your carbon fiber fall. Okay, now high performance carbon fibers, and both low and general purpose and high performance, both of them are used for making composites, CFRPs, as well as CFRCs. So also, by the way, these carbon composites, you can call them CFRCs because, as I mentioned, they are mainly made of carbon fiber. So carbon fiber reinforced carbon. Okay. Now coming to the most important aspect of our, of today's lecture. How do we make carbon composites? So you already know how do we make carbon. Okay, different types of carbon. That is something that we have already learned, that there are many precursors that can be used. You can use resins, phenol formaldehyde resins. You can also use, polymers like PVC, which will rather give you graphite-like carbon. You can also use different pitches, isotropic pitch and mesophase pitch. You know that these are the precursors for carbon. What you need to do is now also add carbon fiber to it. Okay, so that is pretty much it. But there are certain things that you need to ensure. At what time do you add your carbon fiber? How many times you need to reheat it, because you will have porosity, and now here you don't have just general porosity that you had in the case of graphite or in the case of glass-like carbon. What you're also going to have is voids between the fibers. Remember that your fibers, they are already in the form of carbon in the beginning. So you starting with a carbon fiber. However, after you mix it inside your whatever matrix it is, polymer or pitch, when you reheat it, the fibers are also going to be reheated. So they are also going through some microstructural change, maybe some graphitization. And that is why now there is a higher probability of getting voids. Or getting all sorts of defects. So this is what we need to take care of, and that is how we'll do the manufacturing. However, now see this diagram I have taken from this review article here. This is a very interesting article. I think you should read. You will gain a lot of information about carbon composites. So in this diagram, you see in this chart, this is the process flow, that you first take your reinforcement material, that is your carbon fiber. Okay, what do you do now? You can either mix it with a resin, which is typically a thermosetting resin, not thermoplastic. You can also use a pitch as your matrix. Typically that would be isotropic pitch, but you can also use mesophase pitch depending upon your application, what crystallinity, what stiffness do you want in your material. Okay, the third pathway here, that is something we have not discussed for manufacturing large scale carbon materials yet. So this will come, the pyrolysis of hydrocarbons. You know already what it is, but we are going to discuss this more when we talk about the chemical vapor deposition of graphene, for example, or when we make carbon nanotubes. So that is where we are going to go into more details. But you can already see that industrially, pyrolysis of hydrocarbons is also used at a larger scale to make this matrix material around your carbon fibers. So three pathways. You can either take a resin or pitch and then you perform the heat treatment, or you can take your bundles of carbon fibers or whatever structure you want, and then grow carbon, pyrolytic carbon, using hydrocarbon precursors on top of it. And you can grow then several layers, and you can also perform further annealing or hot pressing depending upon what kind of structure do you want. You can also place the entire thing inside an autoclave, and then you can get a certain type of, let's say, sheets. So these are the three pathways that are used. All of them are industrially used for making carbon composites. So let's talk first about your the pathway number one. So you have thermosetting resin, you mixed carbon fiber into it. Okay, now what will you do? You will pyrolyze it. This is called solid phase pyrolysis, because for polymers we are using solid phase pyrolysis. For pitch we call it liquid phase because it's a liquid material. Polymers often they are cured, they are cross-linked, so they are below their glass transition temperature when we are starting, and that is why we would call it solid phase pyrolysis. Liquid phase is pitch, and gas phase is of course hydrocarbons. Okay, so you perform solid phase pyrolysis at between 1000 and 1500. Okay, Now what happens is you do, as I mentioned, that you will get some porosity and some voids will be generated. So what you need to now do is you need to impregnate it with more resin. This is something similar to what we did when we were making graphite structures using needle coke. So you make these needle coke structures, you perform this, relatively low temperature carbonization, and then you get certain pores because your non-carbon atoms are leaving at this point. So you will get some porosity. Now you refill your maybe low viscosity resin into it, preheat it. Still, that that resin will also lose some non-carbon content. So you will again get some porosity. Then again do it. Again do it. So this process can be done, 1 to 4 times, depending upon, how much porosity did you have to start with. So you may have to do this multiple times. You need to impregnate your structure or your overall material with more and more resin, and then keep heating it again. So you can already imagine from here, the materials are very expensive because you're performing very high temperature operations, and not just once but multiple times. Okay, so this is your once you get rid of most of your porosity. You may still have some micro porosity, but most of it is you got rid of it. Then you perform your high temperature treatment. So then you go up to 2200. You can even go slightly higher. So now you perform this kind of heat treatment, and now you get your composite material. Okay, the pathway number 1, same thing but with pitch. The parameters slightly vary because your first pyrolysis that you perform, that is only up to 800 degrees. Okay, and then because pitch and resins are slightly different. Resins are polymers, they have a lot of non-carbon entities, but your pitch may have up to 95% carbon content, and that is why the non-carbon, so the porosity may be less. In fact, the porosity that you get may be more like mesopores or macropores. Even in the case of resin, you will get more micro porosity. Okay, so you perform the first pyrolysis or heat treatment, and then you impregnate it with more pitch. You can also use resin, but you can, in the case of pitch, if you're starting with pitch, then you will do also the further impregnation with pitch, and then again you may have to do it multiple times till you get rid of all your pores or most of them, and then you perform a heat treatment again at 1000 and 1500. This was not the case with polymers, but typically this is done in the case of pitch, and then you will perform your heat treatment, your high temperature heat treatment. So you can imagine that your the pitch based fibers are going to be or the composites are going to be also depending upon the pitch. If you use mesophase pitch, for example, they're going to be graphitic. Okay, and they will also have relatively less porosity. So here we are doing this heat treatment twice because we get these larger pores, larger voids, and then we are filling it again and again, and that is why we are doing the 3-step heat treatment in this particular case. Okay, now the third one, which is the important one, is all of them are important, but important in the sense that we haven't talked very much about it. Okay, so you perform the pyrolysis of hydrocarbon vapors. Hydrocarbons can be again your methane or acetylene, and then you crack these hydrocarbons. Now till now we have only learned that, or whatever little bit we've talked about CVD, we only talked about metal catalyst on which you can pyrolyze or crack these hydrocarbons. But these hydrocarbons can also be cracked at carbon surface itself if your carbon surface is heated. So if you have carbon fibers and the mixture of your carbon surface, so first let's start just with carbon fibers. If you have your fibers, then you heat them, your hydrocarbons can actually crack on the surface of fibers themselves and they can deposit. Then you will perform, as I said, some annealing, or you, depending on the structure, you can perform hot pressing, and then layer by layer you will make your pyrolytic carbon on top of this. This kind of carbon, because you don't have non-carbon atoms, so you are able to control the porosity at every stage. However, you can imagine that this is a relatively much slower process. Okay. Also, the issue is that typically what you want from your hydrocarbon gas is that it will go inside all the pores and voids between your carbon fibers, and because it's a gas, so it should in principle go inside the voids and then crack, and then it can fill all the pores, even including micropores. It should in principle be able to fill all the pores, but often it happens that the top surface gets saturated with the pyrolytic carbon first, and then there may still be some voids inside. So this process needs a lot of optimization, and this process can actually go on for weeks together. So this is a slow and it's also then of course expensive process, but the quality of the carbon that you will get in your matrix material is going to be much superior. So this is these are all the processes that you will use. Now I have one question for you, and you can think about it yourself. At what stage, if you want to provide a certain shape to your structure, let's say you want to make a cylinder using this carbon-carbon composite, at which stage are you going to give it a shape of the cylinder? I think you know the answer, it's easy, but still think about it in all three cases, thermosetting resin, pitch, and pyrolytic carbon structure. At what stage are you going to provide the shape that is desired for your application? So now coming to the applications of carbon-carbon composites, I have mentioned a few here, but you will see that there are many other applications. In fact, while we are speaking, there may be some other applications that people have found, and we have a number of high temperature applications for sure, which also require high strength of the material, high mechanical strength. Okay. Before that, let's just talk about the properties. So when we know the properties of the material, we can find new applications for it. Okay. These are lightweight materials. In their density is in the range of 1.55 and 2 gram per cubic centimeter. Does that sound familiar? That sounds like other carbon materials. So that sounds, now we are in the range where now this is our comfort zone, carbon material. This is a purely carbon material, unlike CFRPs. I mean, CFRPs are great, but they are only 60% carbon, right? So yes, now so you know what is the density of glass-like carbon? It is often below 1.55. And the density of graphite, 2.26. So it is above this range. So now you see that your carbon-carbon composites, they fall between glass-like carbon and graphite, which is also obvious, right? Because glass-like carbons, they have these fullerene-like structures, and therefore they have closed porosity and very low density. On the other hand, graphite has A type crystal arrangement, and that is why it has very good density. What you would expect from something that contains carbon fibers and a relatively disordered carbon matrix, what do you expect from it? So because it is disordered, that means it may have some curved structures. So it may have some, it will not have the density of graphite for sure. It is not a polycrystalline material. You may even have turbostratic carbon fibers. So your density has to be lower than that of graphite, but it is more than that of glass-like carbon, because you are also, you may not have as much closed porosity, microporosity, as in the case of glass-like carbon, because here you also have different structural components, and also you have carbon fibers which were already sort of they did not have so much microporosity as compared to glass-like carbon. Also, several times you performed the densification. So that is why in this range you will get your densities. Other properties, again, now we are thinking of properties similar to other carbon materials. The thermal properties for carbon-carbon composites are the most important ones. So you have low thermal expansion coefficient, okay, and you have good thermal conductivity. You also have good thermal shock resistance, and in fact these materials are used for a lot of high temperature applications. Okay, you can also perform a range of manufacturing techniques, processes with these kind of materials, which you could not do with carbon fiber reinforced plastics, because there again thermal properties become very important. You had very different thermal conductivity of the carbon fiber and the polymer matrix. So there it becomes difficult whenever you're performing any manufacturing operation. Whenever your polymer goes above the glass transition temperature, it's difficult to machine it. But that is not the problem with carbon-carbon composites, because we have very good thermal properties of these materials. So we don't need to worry about, when you're doing manufacturing, you don't need to, the kind of heat that you generate by drilling or milling is not going to do anything to your carbon material. Okay. Applications. So various aircraft, spacecraft applications require high temperature materials which also have high strength. So there are many examples. You can also use these materials are in fact used a lot in high performance braking systems. Okay, engine components, a lot of so turbo engine or other types of engines or components of these the turbine blades and so on. They do utilize, except for there is a problem with oxidation that we are going to talk about it in a while. We'll talk about it. X-ray targets, so there are multiple biomedical applications. You know that carbons are transparent to, or mostly transparent to X-rays, and therefore for a number of purposes we use X-ray targets. Actually, they're mostly made of carbon. They can be used of highly oriented pyrolytic graphite. They can also be made of carbon fiber based composites, carbon-carbon composites. Okay, heating elements, as I already mentioned, for a number of high temperature furnaces and many other applications, the heating elements can be made of carbon fiber composites, because also now their mechanical strength is good and they can withstand thermal fatigue even better than before. Okay. If you're interested, especially this is for the Indian students, India has a national program it has been there for, it has been in place for a long time for developing our own carbon-carbon composites. Okay, and this program has also been quite successful, and the nose tip of Agni missile was made of carbon-carbon composites. Also, several brake pads for light compact aircrafts are often made of carbon-carbon composites. So if you are interested, there are various opportunities. Okay, now coming to the challenges. So one thing I already told you is the oxidation. Other than that, there is one more important parameter, and this is not just for carbon fiber based carbon-carbon composites, but also for CFRPs. This is important. The interface properties. So how well is your fiber or the additive mixed into the matrix? What is very interesting in the case of carbon-carbon composites, I told you that their strength actually increases with the increase in temperature. However, this does not happen for all carbon fibers or all carbon fiber-based composites. If your interface properties are, if you have very good adhesion between your additive and matrix, even in that case your material can fail. So this is also a problem. You need to have there is a certain range in which you need to have your interface properties and the adhesion between the additive and matrix. Only then you get good mechanical properties. So it's not a challenge, but it is something that you definitely need to optimize. So this is one. Number two, oxidation. So all carbon materials tend to oxidize at very high temperatures. Not when you don't think that you will be able to immediately burn these materials. No, that does not happen. If you just have, if you try to even take your the pencil lead and put it on top of a burner, it will become red hot, but it will not burn. So it does not oxidize. It does not immediately burn the carbon materials. But what happens is their surface goes through certain oxidation at higher temperatures, above 450. And also you need excess oxygen. So that is also the case with glassy carbon, above 500, 600 degrees. If you provide excess oxygen to them, then their surface starts to oxidize a little bit. This is a big challenge because you see, we are developing these materials for high temperature applications. So the temperature is always going to be higher than 450. And you are often going to experience, in the case of engines, in many applications, you're often going to have oxidative environment. So this is a challenge. What can we do? The solutions, well, number one is you can make what is known as a thermal barrier coating. So thermal barrier coatings are often used for, even for example, if you make super alloy blades for your gas turbine engines. So you use super alloys, but you also, on top of them, you have what is known as a thermal barrier coating, which is often made of silicon carbide or other ceramic materials. These are thin coatings which prevent your material from suddenly being exposed to very oxidative and hot environments. So this is something that can be done also for carbon-carbon composites. What you can also do, one flexibility that we have with carbon materials and not with super alloys or other materials, is that you can add things inside your precursor before the carbonization. So adding things, and especially when you're making CF based composites, then it's always easy to add things into your matrix. So what you can do is there are certain metal particles that are oxidation inhibitors. So you can add these kind of particles into your precursor, and that is how that also would prevent oxidation of your structures. Okay. Now for further reading, well, there are a lot of books on the mechanics of composites. I have not gone too much into the details of the mechanics because that is, that would make an entirely new course in itself. Okay. However, whatever we have learned till now, some fundamental things about carbon-carbon composites, and also some of the things regarding CFRPs. There are several books you can already see. Here are a couple of articles and books that I have also used, and I have also taken certain pictures from there. The first one, the book New Carbons, that is not just for carbon-carbon composites, but also other carbon materials. For example, porous and activated carbons, and for also just carbon fibers. This is a useful book. The second article by L.M. Manocha, and the third one, Fitzer and Manocha. These are the articles. They are very specific to carbon-carbon composites and the applications, and also many structural properties and the microstructure property relationship of carbon-carbon composites. The last one, the textbook Manufacturing Science by Ghosh and Malik. This is a very useful textbook for all manufacturing related processes and problems, especially numerical problems. This is a book that it's a good gold standard kind of book, and I've also used it myself. So these are some of the this is for your further reading.